So welcome back to this last part of chapter 3. I'm going to go through two related concepts. So that's basically Chebyshev's theorem and the empirical rule. So by Chebyshev's theorem, you have this formula at least 1 minus 1 over z squared minus 1 over, let me just create a new equation here. So at least this proportion of your data, 1 minus 1 over z squared of your data must lie within z standard deviations of the mean. So as an implication of this formula over here, you get the following. So that means at least 75% of the data must be within 2 standard deviations of the mean. So let's just have a look at that. What does that mean? Because we said 1 minus 1 over 1 over 4. Because 2 standard deviations, it means that z is 2. Then 2 squared is 1 over 4. So this gives you it gives you 3 over 4, or 75%. Yeah. So that's what it really means, at least 75%. Then within 3 standard deviations, you should have 89%, which is 1 minus 1 over 3 is 1 over 9. Yeah. So you get 8 over 9. And 8 over 9 is, I assume, is 89%, and so on and so forth. So within 4 standard deviations, you have 1 over, you have 15 over 16. So let's see, 8 divided by 9 is 89%, right? So that is, as a consequence of Chebyshev's theorem, we get these rules over here. But it also means we can actually, with some confidence, compute the percentage of our data. With a fair amount of confidence, we can compute the percentage of our data that is between some bounds. If you have some bounds, for instance, if you have, suppose we have these midterm scores for 100 students, yeah? If you had these midterm scores for 100 students with a mean of 70 and a standard deviation of 5, then we can know with certainty how many students are going to be between, we can know with certainty how many students are going to be between 60 and 80. So we have to compute the z-score. For the lower value, the z-score is going to be the value minus the mean of 70. So that's 60 minus 70 divided by the mean, rather the standard, divided by the mean over the standard, rather minus the mean over the standard deviation. It gives us 2 standard deviations, or minus 2 standard deviations. Then the between 60 and 80, we said. Then the 80 gives us something similar. 80 minus 70 is over 5. In this case, we get a positive 2. So you see, this value is actually within 2 standard deviations of the mean. So from Chebyshev's theory, we already know that this is going to be 75% of students should be between this value, because this is 1 minus 1 over 2 standard deviations squared, 4. So that gives us 3 over 4, or 75%. So we know that 75% of our students are between 60 and 80. Between 58 and 82, again, we can compute with a fair degree of certainty the number of students that are between this. I think this is now so the mean is between the mean is 70. The mean is 70. So 58 minus 70 equals 58 minus 70 is minus what? 58 minus 70 is a minus 12, right? Minus 12 over 5 is 2.4. 2.4, then between 58 and 82 minus 2.4, yeah. Then the 80 minus 70 is 2.4. 80 minus 70 it gives us 12. So minus the standard deviation of 5, you get another 2.4. So to get the percentage, that is going to be 2.4 squared inverse. How do I get the inverse here? 1 divided by 2.4 divide by 2.4 again, minus 1. So at least 82%, of these should be, if you round off, at least 83% of the students should be within this range, and so on and so forth. So if you have a bell-shaped distribution, then the Chebyshev theorem will give rise to the empirical rule. If you have a bell-shaped distribution, so this could, for instance, if you have the normal distribution, is an example. It's a famous example of a bell-shaped distribution. Then the Chebyshev theorem will directly result into the empirical rule, which basically gives you these values. So this can be useful if you want to get outliers, for instance, because in general, almost all your data, almost 99%, should be within 3 standard deviations of the mean. So in general, if you want to get outliers, you could use this approach. An alternative approach is to use the 5-number summary. 5-number summary. 5-number summary. So you do this in conjunction with box plots. So for the 5-number summary, you want to have, first of all, the smallest number, or the lower limit. Then you want the Q1, Q2, Q3, and then you have the largest number. So the smallest number is actually 1.5. Is this Q2 is going to be Q2 minus 1.5 times the IQR, the interquartile range. So that's where you get the smallest number from. Then the largest number is going to be the median, right? Q2 plus 1.5 of the interquartile range. So if you want to visualize this, you normally use a box plot. So this is the upper limit. It has 1.5 the IQR, and then this is 1.5 the lower limit. So anything that's outside these bounds, outside lower than the lower limit or higher than the upper limit, is called an outlier. Alternatively, if you use the empirical method, then an outlier is going to be any value that is more than 3 standard deviations from the mean. So there are two approaches that you can use to detect outliers in your data. Both are very widely accepted. Why do we want to detect outliers? So usually if you have outlier data and you're doing an analysis, sometimes it's better to remove the outlier data. Outlier data usually means that there's something wrong with the observation. Maybe you made a mistake in sampling or in data collection. And these values are capable of changing. For instance, of influencing the mean. If you have a very large outlier data points, a few of them can actually shift the mean. For instance, these outliers, if they're on this side, a few of them can actually shift the mean towards this side, and a few of them could shift the mean towards this side. So, especially if you're doing measures of variance of centrality, you want to get rid of the outlier data of location and centrality of variance. You want to get rid of the outlier data because it can actually bias your data set towards a certain direction. And usually, it's often the case that these outlier data points are, it's usually there's a need for you to actually take a closer look. Usually they indicate that you've probably made an error. For instance, we had like when you were doing COVID statistics, if you found one small country called Uganda, where the percentage of people who are dying in under 30 is extremely high compared to the rest of the world, then it is likely that in Uganda there's the testing, some errors are being made, the data is not clean. Yeah. So most of your data should actually be within free standard deviation. So if you have data that is wild, that is not conforming to what you expect, then it's better you remove that data, because most likely it is an indication that there's a mistake in that data, and the only thing it's going to do is to actually bias your conclusion. One more thing, I did make a small mistake when I gave it the formula for skewness. I leave it up to you to find out where I made the mistake. So that ends chapter 3.